Alright, welcome to the second video with enzymes. I know we talked a little bit about the basics of enzymes in the previous video, and now we're going to kind of turn things up a notch. That first video was really just to kind of give you a review, and now we're going to talk a little bit about kinetics. And so it's important to understand that the rate of a reaction, so the speed that the reaction occurs, is the reaction velocity, and that's denoted by V. And that reaction velocity is dependent on a few things. It's dependent on the enzyme concentration, the substrate concentration, the temperature, and the pH. So we're going to go through these one by one. The enzyme concentration, as you can see here, as we increase the amount of enzyme that we have, we're going to increase the rate. In some fashion or another. So usually you'll see that type of linear dependence. But when you're looking at an increase in substrate concentration, usually this will end up leveling off at some point. And so you might wonder why that is. And the reason for that is because eventually all of the enzymes will be used up. And when all the enzymes are used up, there's nowhere for the substrate to essentially bind to undergo a reaction. So if you keep adding enzyme, right, and you have some unlimited number of substrate, you can continue to increase the reaction rate. But if you increase the amount of substrate you have, but you don't increase, and you only have a set number of enzyme, eventually all those enzymes will be working and there'll be no one available to accommodate the new substrate that you're putting in. And so that's why we get this leveling off here. Okay, that's the saturation. Okay, so here we're at the temperature. And so, yeah, when we increase the temperature, the molecules will be, have more kinetic energy, and we can increase the rate of our reaction. And you can see that here as I increase the temperature, we are increasing the reaction rate until we get to an apex in which the protein or whatever enzyme we're dealing with can no longer function at a certain temperature, and then we see a much steeper decline, and that represents the denaturation of the enzyme because it can't function under those kind of conditions. Much it's in the same way as when we denature an egg, right? We heat it so it's so hot that it's the proteins are completely denatured. Well, the same thing is going to happen with an enzyme when we put it at some temperature. So a little bit different type of reaction rate graph we get with temperature. But the pH, you can think of it in the sense that, on a protein you have so many positive and negative charges, and all of those, charges have to be in place. And there's some optimal pH that will represent the appropriate protonation and deprotonation of the various amino acids and whatnot on that protein. So when you veer away from that optimal pH, wherever that is, you will begin to lose functionality of the enzyme and therefore decrease the reaction rate. Okay, so those four factors are all factors you kind of want to try and keep straight in terms of their graph and their function. And so let's take a step back now and look at the enzyme substrate reaction. So E enzyme plus S substrate undergoes a reversible reaction in which you form this enzyme substrate complex. Okay, and that enzyme substrate complex then would technically undergo an irreversible reaction with enzyme plus product. But a lot of times what biochemists do is we don't really look at the reverse of this, because we just assume that we're starting a reaction from the very beginning and we don't have any product yet. So therefore this equilibrium will just be going towards the product, right? If I don't have any product, this reaction is just going to move in this direction, so I don't really worry about this other arrow going back. So essentially, when I get to this enzyme substrate complex, I can go either way. I can either go back to form the enzyme and my substrate, or I can move forward to form my enzyme and my product. And then you can see this is the catalytic step, and this step refers to the substrate physically binding to the enzyme. Now, one kind of added point here that is a little above the scope of this is that if you have a really low Km, usually that can mean that this enzyme substrate is easily formed, right? If I have a low Km, which we'll see in a minute, that means that this binding will occur very readily. And that can transition me into this next point, which is the Michaelis-Menten equation. And if you haven't heard of Km just yet, I'm going to go through that here in a minute. But essentially, let's start at the beginning. I'll backtrack a little bit. So we have V is equal to the velocity of the reaction. We talked about that. And if I'm looking at this graph, I can see in the x-axis I have my substrate concentration, and here I have the reaction velocity. And I remember from the previous graph that we have that I showed you that the substrate concentration eventually becomes saturated, and that represents this leveling off here. So I'm increasing the reaction rate, and then when I get to some point, all my enzymes being used up, and then I'm reaching saturation. Well, that saturation that I reach is the Vmax. It's the maximal velocity of the reaction. I'll never actually reach the Vmax. It's an asymptotic approach that I make towards it, but I can get awfully darn close. The substrate concentration usually has these brackets. As you remember from general chemistry, this represents concentration. And then the Km is just the maximal speed of the reaction divided by 2. And so that's what the Km represents. And you can see if you have a low Km, that means that you can reach half of your maximal speed very easily. So in other words, let's go back to the previous slide. If you have a low Km, you can very easily reach, you can very easily get to your products, right? If you have a low Km, because if you have a low Km, that means that you'll need very little substrate concentration at which you reach this Vmax over 2 will be very low. One thing that always confused me when I was looking at this, because I had to really look at this a few times, is that the Km is a concentration. It's some number that is an actual substrate concentration. So the Km is the substrate concentration at which the maximal speed of the reaction divided by 2 occurs. Okay, so the Km is a substrate concentration. The sooner you understand that, the easier this becomes. And so once again, I'm going to repeat that the Km is for a reaction. If the Km is very low, right? If the Km is very low, then I don't need a lot of substrate concentration to reach half of the maximal speed of the reaction. If my Km is really high, then I need a lot of substrate concentration. If my Km is way out here, I need a lot of substrate concentration to reach half of the maximal velocity. So things with low Kms are very sensitive to reactions, whereas things with high Kms, you really have to add a lot of substrate to get the reaction to go. Okay, now this equation is the Michaelis-Menten equation. So we have the speed of the reaction is equal to the maximum speed times the substrate concentration divided by the Km plus substrate concentration. I'm not going to go over the derivation of this. It's not important, but it is important that you understand this reaction and understand what happens when this reaction has a low substrate concentration as opposed to a high substrate concentration. So I'll leave that task for you to kind of mess around with what this thing will look like with low and high substrate concentrations. But some of that is a little beyond the scope of what I want to cover in this video. So the next thing we're going to look at is a linear representation of that equation. And so here, this is called a Lineweaver-Burke plot, and it makes things easier even though it looks a lot harder at first. So let's just look at the y-axis. The y-axis is 1 over the reaction velocity, and the point that we cross this axis is 1 over Vmax. Okay, so if I wanted to find Vmax, I would just find where my line, my reaction crosses the y-axis, and then I would just take, I would set that number equal to 1 over Vmax, and then I just solve for Vmax, and that would give me the maximal velocity of my reaction. Conversely, if I wanted to know what Km was, the Km of my reaction, I would just find the x-intercept in this case and set that number equal to 1 over km. If that was a negative number, I just set it equal to 1 over km. I'm sorry, negative 1 over km, and I would be able to solve and figure it out what my km would be. So the x-intercept is 1 over km, the y-intercept is 1 over v max. All of these y plots are just the reaction velocity, and all of the x plots is just 1 over the substrate concentration. So 1 over the reaction velocity, 1 over the substrate concentration. And if you think about it, therefore, then the slope of this line must be the km, right, the rise over the run, which is v max. So a lot of this you can derive, or you can just memorize it, but you'll see in the next few slides that the Lineweaver-Burke plots are commonly tested on medical exams in your first couple of years, and so it's very important that you understand this. So the reason that we look at Lineweaver-Burke plots is because it's very easy to obtain data from, you'll see for these inhibitors that we'll be talking about, you can really distinguish which type of inhibitor and which type of interaction is occurring, through some practice of looking at these. So the first inhibitor we'll talk about is a competitive inhibitor. And what a competitive inhibitor does is it increases the Km. So if you remember, if you have a low Km, that means it's very easy to get a reaction to go because you don't need a lot of substrate concentration. But here, when you have a competitive inhibitor, if you think about it logically, right? I have this substrate. I'm sorry, I have this enzyme and I have this substrate that binds here, and I get my product. Well, when I inhibit it with some other guy that can fit into that slot, now he can't bind anymore. And so I'm going to need more substrate. I'm going to need more of these guys, right, these green guys, so that they can get to this spot before this inhibitor. And essentially, when this guy gets dislodged, they're going to take that spot. So if I get more and more and more substrate, it's going to be less and less likely that the inhibitor will be able to bind. And what I'm doing is I'm requiring more substrate to get the same reaction. And so when I'm using a competitive inhibitor, what I'm doing is I'm requiring a greater substrate concentration to reach the maximal speed of the reaction, or half of the maximal speed of the reaction. Therefore, I'm increasing the Km because I can't get half of the maximal speed of the reaction anymore because I have these guys floating around, at that same substrate concentration. I need more substrate so I can competitively compete with these guys and get them out of there. And notice that the maximal speed of the reaction doesn't actually change. The maximal speed of the reaction takes more substrate to obtain, but it doesn't actually change. So, because we have the same amount of enzyme and the same, and we do have more substrate, but we always have the same amount of enzyme. That never changed. So we can still only reach the same maximum. Hopefully that makes sense. I know it's kind of confusing. Doing my best to explain it to you. So this black line obviously is no inhibitor present on my Lineweaver-Burke plot, and my pink line is competitive inhibitor present. And if you look at where they're at here on this x-axis, the no inhibitor present is going to be back towards the left, and the no inhibitor present has a lower Km. So let's just say that with the no inhibitor present, our Km is 1, right? So this intercept is 1 over the negative Km. So 1 over negative 1 is just negative 1. So this would be negative 1, and let's just say, the competitive inhibitor's Km was 2, right? It's going to be larger. So, this would be negative 1 over 2, which is negative 1/2. So you'll see that the competitive inhibitor is going to get closer and closer and closer to this because it has a bigger Km. And when you plug it into that equation here, you plug it in here and you have a bigger and bigger Km here, it's going to push this line closer and closer to 0. And so that's why that is. And you'll also notice that they both cross the y-axis at the same point. And remember, that point is 1 over Vmax. And so that means that, like we talked about, they have the same maximal speed, even if they both have different kms. They still have the same maximal speed for the reasons I mentioned earlier. Okay, these are non-competitive inhibitors, so a little bit different. These inhibitors essentially function by inhibiting the enzyme or the complex here, but they do it by binding outside of that active site where the substrate binds. So they bind outside of that site, so they don't compete necessarily with the substrate. That's why they're called non-competitive. And in doing so, by inhibiting these guys, they actually form their own little molecule, like an enzyme inhibitor complex. And so you can see that all these enzyme inhibitor complexes are taking away from the actual reaction we're trying to get, which is get to this product. And so the fact that we're taking all of these complexes and we're kind of going on this alternate pathway, we're actually decreasing the maximal speed of the reaction because we have less enzyme available. Essentially, any time you mess with the enzyme, you're going to affect the speed of the reaction. Notice here that we never change the enzyme, and when using competitive inhibitors, we never change the enzyme. We just changed the this inhibitor and this inhibitor that binds to it. We never actually changed the enzyme. That's why the Vmax stayed the same. But here we're actually, taking enzyme kind of out of the mix and inhibiting it, and that's why the Vmax decreases. Interestingly enough, the Km is the same here. And the reason that the Km is the same here is because nothing is actually inhibiting the substrate binding, right? Nothing is inhibiting that directly. The substrate's not competing with anybody, and so the Vmax over 2 will actually be the same. Okay, and you can see that here. Km is the same, and you can see that the Vmaxes have been changed now, indicating this one's decreased. I know it's kind of confusing. It looks like this one's greater, but remember, this is 1 over the reaction, right? This is 1 over Vmax. So yes, this Vmax is smaller, but because this is 1 over Vmax, it's actually going to appear to be higher up. All right, now we're going to talk about irreversible inhibitors, and these guys essentially, you'll see this with phosphorylation, acetylation, a lot of different techniques that metabolic pathways use to shut down an enzyme. And so here you can see you can't really see the text, but this is DIP, which we'll talk about at some point possibly, that binds irreversibly to the serine residue. Serine, I think this is 195. Oh, don't quote me on that. That's probably wrong, actually. But it binds to the serine residue, and you get this complex. And now this serine residue can no longer function in its pathway because it has this massive molecule on it. Okay, so, and the thing to note about irreversible inhibitors is they're very similar kinetics to the non-competitive inhibitors, okay, in the sense that they decrease the Vmax and have a similar Km. Okay, not always the case, but very similar in that sense in a lot of cases. Okay, regulatory enzymes in metabolic pathways. We're going to talk about a lot of these. The example that I put down here. Well, first off, let me state that this is not a Lineweaver-Burke plot. This is a hemoglobin partial pressure of oxygen on the x-axis, and then the y-axis is the saturation on the hemoglobin molecule with oxygen. And so you probably have seen this before. I'm sure when you took your MCAT or whatnot, you might have seen it. And I just noticed this is kind of spelled funny. This fetal. I think it's supposed to. I don't think there's supposed to be an O there, but hopefully you can forgive that. But essentially, here we have hemoglobin, and the important thing to note is that the hemoglobin obviously has 4 sites for binding oxygen, and you can see that it's almost like a cooperative binding. When one guy binds, then another guy binds, and then as more and more guys bind, this curve spikes up. Whereas myoglobin, who just has 1 site, doesn't have the 4 sites like hemoglobin. He represents more of this I don't know, it's a different shaped curve. It's more like a parabolic type curve, whereas the hemoglobin is more of a sigmoidal type curve that it has. And so I guess the moral of the story here is the allosteric or regulatory pathways usually have these sigmoidal curves, whereas the enzymes that only bind like one thing, only have one binding site, and then there's not really any cooperative binding, look like myoglobin. And a lot of times we say that those enzymes that have multiple sites function through allosteric interactions that bind on different parts of the protein or the enzyme. And so most enzymes are kind of going to look like this hemoglobin. And you'll notice they're going to have nonlinear Lineweaver-Burke plots. So they're not going to be similar to what we've seen. And it's just because of the cooperativity and the allosteric binding that you see on them. So here's the follow-up question, and it's I guess my only advice is, you know what, I'm not really gonna, I don't want to give away too much, but I will say hopefully if you've taken the last follow-up question on the previous group of slides that you've an enzyme basic PowerPoint, you've kind of starting to get used to some of the terminology and you know, kind of reading through some of this stuff. So do your best. I'm gonna count to 5 and then I'll go through the answer with you, and you know, hopefully that will hopefully you'll get it right. 5, 4, 3, 2, 1. And so the answer is C. The irreversible inhibitor to the COX enzyme is what the aspirin is most likely acting as. So this is all true, pretty much all of it here. Yep, all of it's true. And essentially, I mean, here's the deal. I mean, we just don't want to get wrapped up with all of the other information. So, you know, this line here, this feature distinguishes aspirin from diclofenac and ibuprofen. You know, okay, cool, but you know, this doesn't really. I mean, yeah, it's interesting to know. It's important to know actually when you know, as soon as we move into the drug section and the hematology. Yeah, this is something we're definitely going to talk about. But I mean, it's, you know, it's not. It has nothing to do. You know, the competitive inhibitor to diclofenac and ibuprofen drugs this has nothing to do with, you know, with these statements. So these statements, I mean, automatically should be able to rule A and B out because there's no indication that aspirin has anything to do with, aspirin has no type of inhibiting effects on diclofenac or ibuprofen. That's not said anywhere. It's just kind of made there to mislead you. In fact, I think I just needed some extra variables here to put in to you know, make the question. So these should be easily ruled out. You know, and if they're not easily ruled out, maybe read through this again, and hopefully you'll see why they're not a major part of the question. Let's look at C, irreversible inhibitor to the COX enzyme. So if you remember, and I'm going to go back a few slides here, we said that irreversible inhibitors are similar to non-competitive inhibitors. And a non-competitive inhibitor, if you remember the Lineweaver-Burke plot, we had a decrease in Vmax represented here, and we had the same Km. And so if I look at this graph, I have the same Km. I even kind of give you an arrow to give you a clue, and I have different Vmaxes. And if you look, the red line is the COX enzyme in the presence of aspirin and without aspirin in green. So I think that is basically a dead giveaway. It's acting as a non-competitive, or acting similarly kinetically to a non-competitive inhibitor. Okay, if you think about it, if something's irreversibly inhibited, it's going to decrease the maximum velocity of the reaction, right? And that's what happened here. D, competitive inhibitor to the COX enzyme, right? This is not a competitive inhibitor because a competitive inhibitor would have the same Vmax. So off the bat, you know that's wrong, and it would actually increase the Km. So you know that's not right because they have the same Km. And an uncompetitive inhibitor is actually one that we didn't talk about. An uncompetitive inhibitor actually decreases Km and Vmax, and this is something that I don't see a lot of it in the USMLE books, but if you want more information on that, you can probably look it up. It's it's very similar to the inhibitors that we've talked about. So hopefully you got that one right, and I'll see you guys in the next video.